Here we're going to look at GCSE reflection. So everyone knows what the basic idea of reflection is because we all look in mirrors. Of course, for GCSE we need to be really careful to use the formal definition. We need to know the definition of the law of reflection, which is that the angle of incidence, so the angle the light ray comes in at, is equal to the angle of reflection. So what does this look like on a diagram? So we will have our mirror. Often it has a sort of dashed line on it like this to show it's a mirror. We need to draw on the normal line. So this is the line at 90 degrees to the surface. Also very important when we look at refraction. Students will often get a little bit confused here. They'll often say, how do I know at what point I need to draw the normal on? The best answer is where the light ray hits the surface, because this is a normal, this is a normal, this is a normal. There are an infinite amount of normals, but we care about where the light ray hits the surface. So we're then going to draw our light ray coming in. Make sure you put an arrow on our light ray reflecting, and importantly, the angle of incidence is the angle between the light ray and the normal, and the angle of reflection is the angle between the light ray and the normal. Okay, students often put these angles. That is not the correct angle. So for regular reflection, these two angles are equal. At this point, students may also get confused. They might say, well, hang on a second, light travels in straight lines. That's one of the first things you taught me. But light is clearly a wave like this. So how is that a straight line? So now it's important to refer back to the definition of a transverse wave, where we say that the particles are oscillating perpendicular to the direction of motion of the wave. So the red line here is the direction of travel of the wave, whereas the black line is the oscillations. Now with light, obviously it's not particles oscillating, it's the electromagnetic field. But it's still true that the oscillations are up and down, but the motion is perpendicular. So this type of reflection here is known as specular reflection, where we form a nice image on a smooth surface. So important facts are that the image is the same size. It is a virtual image. That's more important for triple. A virtual image is one that you can't project onto a surface. And it's importantly also the same distance from the screen. This is basically just another way of saying it's the same size. And then the image, as well as we know, is flipped left to right, but not up and down. So you can have a nice kind of discussion with students here about why this is, and it does make them think. And the answer is relatively straightforward if you kind of sketch some kind of diagram. So obviously light comes in and it comes back at the same angle. Light of the other side comes in and comes out. If we look at light from the top and bottom, it comes in, it comes out. So it's literally just giving back or reflecting the light exactly where it came from. So obviously anything that's on top stays at the top, anything on the bottom stays at the bottom, anything on the right stays on the right, etc. But because you've then reversed the image, you're looking out of the mirror rather than looking in, it appears like you flipped left and right, but it's not doing that as such. It's just literally moving the light back where it came from. So we can show all of this on a ray diagram. Now this again is more triple, but it is worth showing students as well. So we've got some image here, and the light rays are going to come in. I'm going to draw two this time. Now students should always use a ruler for drawing a ray diagram, so I'm being a bit naughty here, not using a ruler. But we're going to have our light rays coming out, and then we've got our image here, which is going to be the same distance from the screen. And obviously we know that this angle is going to equal this angle. Where does this image appear to come from? It appears that it's come from behind the mirror. It actually appears that it's come from up here. All right, and if I'd drawn this properly with a ruler, you'd see that this distance equals this distance, and obviously this distance equals this distance, hence it's the same size, same distance from the screen. And you can see that something on the left-hand side now appears on the other side, right, relative to somebody looking. The other type of reflection is diffuse or scattering. So here you've got a surface that is actually not entirely smooth. So when we have some light rays coming in, I might draw 4 light rays, they're going to obey the law of reflection, right? The angle of incidence is going to equal to the angle of reflection, but because it's a rough surface, the light rays will actually come off, reflect at completely different angles to represent the fact that the surface is not smooth, so you don't get a clear image. You can show examples of this really easily in a classroom. You can look at a piece of laminated paper, you can look at shiny pencil cases, water bottles, and show this effect. And then the last thing that's worth mentioning is just a couple of common situations that students will be asked to show in an exam question. So the periscope is one of the most common ones. So we have 2 mirrors like this. Often there'll be an eye here or a person, and there'll be some image here. And then it will be, something like complete the rays here. So again, using a ruler, students complete the ray diagram. They need to draw it going into the eye. They need to label it with arrows in the correct direction. So obviously going towards the eye, no laser eyes here. All right. Usually 2 rays is sufficient. And again, with a ruler, so it's a bit neater than my one. Another common example would be some object like this at a right angle. And this is quite nice because it is obviously a nice example of reflection where students have to complete a slightly more complicated situation where obviously this angle is equal to this angle, although for students it's a lot easier to make these angles equal, even though that's not technically the angle of incidence reflection. This has a nice practical application, this shape as well, because if I draw a light ray coming in at a much steeper angle and then draw it relatively carefully, what you'll find is actually the light rays will always emerge parallel to the one that comes in. So you can extend this, you can say, imagine a cube and imagine the inside corner of a cube, so this corner here. If you build one of these, any light ray you shine in will always come back at the same angle. And these are used in reflectors on things like bikes or high visibility jackets that are really shiny or cat's eyes. And there's also a nice use for engineering as well, where you can stick them on buildings, you can shine lasers, and you can work out distances really, really accurately. So it's a nice practical application of this. You can obviously also do a practical with students. You can get them to investigate this with mirrors, protractors, sharp pencils, etc. Relatively straightforward practical, doesn't take that long, but it's a good chance to demonstrate their practical skills and obviously prove this to themselves.